Welcome back. In this section, I want to give you a brief overview of the main ideas of the course we're going through. We're going to talk about the material for test one. This course is based on 4 sections. The first section, where are we, looks at local geology, small scale geology, and the second part looks at big scale, where we want to be, like Hawaii or California or places like that, looking mainly at plate tectonics. The third section looks at what are the hazards if we move to one of these locations. And the fourth test material looks at what are the resources that are available to us when we get there. So, excuse me, when we talk about local geology or geology in general, we need to think about 3 main things. The first is the main focus of this class, which is physical geology, understanding processes. Uniformitarianism, which we want to make sure we understand, the idea that we look at the things that are happening now to try to understand how the past came to be the way it was. And we also try to avoid catastrophism, which is superstitious explanations of things, blaming people for bad things happening, like when I talked about Hurricane Katrina. Second thing we need to understand is a little bit about historical geology, specifically geologic time, evolution of landscapes and organisms. For example, how glaciers in the past have shaped the landscape. And the third thing we need to understand is the scientific method, making observations, trying to see if there are any patterns, making a guess, which we call a hypothesis about those patterns, then testing it. It's not scientific if we don't test it. But if it passes the test over and over again, lots of times, it becomes a theory instead of an hypothesis. Well, as I've told you before, I use a lot of stories in class. And if you think about the scientific method, you think about geology, any good story has place, time, and plot, right? Where it happens, how it happens, and the change over time. So I hope the stories that I tell you along the way will help illustrate some of these key parts of geology. By the way, if you look at the picture on the right, what you're looking at there is a picture I took when I was in Austria teaching many years ago. You see the white line coming down the middle, a little stream there. Well, a glacier went down the main valley from left to right many years ago, cut that valley down, but left hanging a little bowl up near the top here where a smaller glacier came in, and now they've all melted off and left this hanging valley that we call it, where the stream comes out. Really beautiful. So, first concept we need to understand when we're looking at geology is the idea of age dating. Break it down into 2 parts, relative and absolute. If you look at the relative, we look at things like fossils, we look at layers of rocks. For absolute, we look at some way of telling time. So let's look at those in a little bit more detail. When we talk about relative dating, we're talking about younger or older, not how many years, simply younger or older. So the easiest way I mentioned before to think about this is like coming in every day, throwing down the mail. Come in, throw down the mail. But don't look at it, just throw it down. Well, in a week's time, if you got a big stack of mail, where's the oldest mail? Down at the bottom of the stack. When we go over to some place like the road cut in Wisconsin, and when you cross over the Wisconsin Bridge and go in toward Keeler, that area, you see layers of rocks along the road cut, like where I'm pointing at there. Well, the rock layers near the top are going to be younger than the ones down towards the bottom. We also know things like cross-cutting relationships. There's a crack, like I'm pointing to here. That crack came later than the thing that got cracked, right? Most sedimentary rocks settle out of water, which is fairly horizontal. So the rocks are generally originally horizontal, but tectonic processes we'll talk about later can deform those shapes. Inclusions mean the things that we find inside of the rocks, like fossils. So in these particular ones, we find some shells. So those shells have to be older than the rock that they're in. Think about it like a layer of concrete. The gravel that's in the concrete is older than the concrete sidewalk. And then fossil succession. If we find a fossil of a dinosaur and we find a fossil of a cow, well, the rocks are a lot older that have the dinosaur in them. So all these things come together to help us figure out what's older and younger. Not just one, but look at them all together. We'll do some more stuff with this in the lab, so it'll help you to solidify these concepts. We're not going to memorize them. We're going to use them for distinguishing younger and older. When we look at absolute dating, we're trying to figure out time. Now, we're used to telling time by things like days and years and stuff like that. Anything that occurs regularly, right? The sun goes up and the sun goes down. The seasons change, right? Related to the spinning of the earth and the orbit of the earth around the sun. Well, to tell time for a geologist, we need something very similar, like a pendulum and a clock, only lots slower. So what the geologist uses is what's called radioactive decay. Radioactive decay depends on the analysis of isotopes. An isotope is an element, like carbon, like oxygen, and each isotope has a particular weight. So let's see if we can narrow this down. All three of these are carbon nuclei. So if we look at carbon, it has 1, 2, 3, 4, 5, 6 protons. Protons are positively charged in the nucleus of the atom. That 6 protons determines that it's carbon. Every carbon has 6 protons or it's not carbon. But it can have a different number of neutrons. Neutrons are neutral, no charge. So if there are 6 neutrons, 6 plus 6 makes 12. So we call that carbon 12. If we have 7 neutrons, 7 plus 6 makes 13. We have a heavier version of carbon, carbon 13. And then if we have 8 neutrons, 8 plus 6 make carbon 14. Okay, these are all carbon because they all have 6 protons, but they have different number of neutrons, and the number of protons plus neutrons determines the isotope of the element. But as we look at that nucleus, not all of them are as stable. This fat carbon 14 with more neutrons, not stable. Over time, that neutron changes into a proton. It gives off a particle that changes its charge. Now we have 7 protons. It's not carbon anymore. It becomes nitrogen. So it actually changes the type of element over time at a very regular rate. Carbon 14 turns into nitrogen at a rate of about 5,730 years for half of it. Half of half is a quarter, so that's another 5,730 years. Half of a quarter is an eighth, and so on those lines. So if we have very precise equipment, we can look at the ratios of carbon in our any living organism, like old piece of wood from a Native American ruin out in the southwest U.S., anything along those lines, old bone fragments and stuff like that, to figure out how old something is in years. That absolute date then tells us how old something is in years. The geologic time scale was built originally based on relative dating. We've since added absolute dating to it, but the key things about the geologic time scale I want to go through. First is the Precambrian. The Precambrian that we saw a little bit earlier in this course is the time period where anything that was living didn't have hard parts, so like bacteria and stuff. It was there, but geologists couldn't see the evidence of it back in the old days because we didn't have the equipment. There were no shells, no hard parts. Well, when the first hard parts started showing up in the rocks, that's when we moved to the Paleozoic, old life. This is the Paleozoic, all here in blue, right? Then when the reptiles arose and dominated, especially the dinosaurs, the Mesozoic time period represents the time of the dinosaurs, like the Triassic, Jurassic, and Cretaceous. And then the Cenozoic is the time when the mammals began to dominate. So within the Paleozoic are a couple of layers of rock that are important for us here. The Ordovician are the ones that are right under campus. The Silurian ones, a little bit younger, are the ones that are underneath the airport. And you notice as you go towards the airport from here you rise up onto a higher level. You've come up on top of the Silurian age rocks. We'll look at these in more detail in lab also. So here in Dubuque, we're on top of Paleozoic rocks, Ordovician here on campus, Silurian underneath the airport. But up on the top of the Iowa, most of Iowa, not where we are right here, but just a little bit west and all the rest of Iowa, is evidence of the glaciers, which came much, much later, really relatively recent time. It's called the Pleistocene. We'll go into that in more detail as we go through Iowa geology. So this is a relatively young skin of material that was left behind by the glaciers that covers over a lot older rocks. There's another use for isotopes for telling past temperatures. Oxygen comes in a couple of different isotopes also. There's skinny, smaller oxygen, and there's bigger, heavier oxygen. Well, oxygen combines with hydrogen to make water. And so when water evaporates, the water that's made with the oxygen 16, which is the smaller, evaporates more easily than the oxygen 18 water. So what happens is it moves up into the sky, falls down as rainfall, flows back to the ocean, which is all fine, except during ice ages, when it cools off, a lot of that water gets stuck in the expanding glaciers. And so the ratio of O16 to O18 changes within the oceans and within the glaciers as well. And so we use that to tell whether it's a time of cold or a time of a hot period going on. We'll talk about that more in the Iowa geology section. Within the earth, well, we live on the outermost scum, which is the very top part. It's relatively thin. It's cooled off relative to what's inside, so it's brittle, so it breaks. It's called the lithosphere. And that lithosphere then, as it breaks into major plates, is what causes the plate tectonics. Underneath it is a fairly toothpastey type layer, the asthenosphere, which allows that outermost brittle part to move around. Inside it gets warmer and warmer until we get down to the outer core, which is melted. It's a liquid. But when we get to the inner core, the pressures are so great and the material is mostly iron and nickel that it's solid again. How do we know what's inside the earth? Well, we haven't drilled anywhere close to like a mosquito bite on the surface, right? We haven't gone down there, but sound waves penetrate down. Just like an ultrasound can see a baby inside of a mother's belly, sound waves go down and see inside of Mother Earth's belly and tells us what's going on down deep within the earth. As I said, that scum's in motion. It's moving away, coming together, sliding by in a variety of locations around the earth. And so there's some major plates with a lot of little small ones as well. And so we'll be talking in section 2, mainly for test 2 is about those plate tectonics. So we're sketching together the rock cycle. You'll find it in the book. There's a picture there that you can take a look at as well. 3 main rocks, rock types. That's igneous, metamorphic, and sedimentary. We'll look at those in lab a little bit later on. They all form in different ways, and so understanding them is really super important. So take a look in the book at the rock cycle. We'll draw it together in class. We'll also sketch the Mediterranean Sea, reasons why we think the Mediterranean Sea was a desert, not a desert, but a desert. And the reason we do this is to show how a geologist goes about figuring out the past. We've taken boats out into the Mediterranean Sea, here in blue, drilled down into the ocean bottom through mud, into old sand dunes, into layers of salt. And so we put together the story. So there's also a diagram of that in your book as well. Notice that the Mediterranean Sea connects to the Atlantic with a little small opening at the Straits of Gibraltar, and it's pretty shallow. So when ocean levels dropped in the past, it cuts off the Mediterranean Sea from new ocean water, and so it has gradually dried out. We put that evidence together based on those drillings I was just talking about. And then last point, while we're reviewing here, just remember, go to your book, pull up those review questions, follow along as we're working our way through the material, and that'll help you out when it gets time for the test.